All right, welcome everyone to this instantiation of the Long Range Colloquium, which is hosted and organized by the Virtual Science Forum. Before getting into today's meeting, I'd like to announce that the Virtual Science Forum will be hosting a workshop on Andrea reflection in quantum Hall systems on December 9th. It's organized by myself, Anton Akhmarov, who's here, and Christian Schonenberger. So anyone who might be interested can find a link to the workshop webpage in the chat. But today we're excited to have Professor David Goldhaber-Gordon from Stanford. I've personally long enjoyed following his group's work, which has spanned a wide range of interesting topics from mesoscopic physics, 2D materials physics, topological phenomena, and more. Today, I think, as David mentioned in the chat, that he'll be discussing an interesting kind of open question topic, and I'm excited to learn about his thoughts on the matter and see where this takes us. If you have a question during the seminar, you can please use the Zoom's raise hand feature, and then I or another host will call on you at a good moment to present your question verbally. David, take it from there.
Thanks very much, Vala. And I just want to amplify what Vala said, that I am happy to answer questions during the course of the talk, and especially if it's something that you're not understanding or you think that a point could be usefully expanded. So if there's something that's sort of a side comment or curiosity, feel free to leave it to the end. But if there's something that you think could change how you and others are interacting with the talk, then please don't hesitate to jump in during the talk, because there are probably other people who are puzzled or who could benefit from that. So I've been in some form thinking about for more than 25 years the question of what is a quantum simulator, and this began for me with I guess late in my undergrad time, when I was exploring what I wanted to do for grad school, and I went to a series of talks, and I'll explain how that affected me. But so today I'm going to explore what I think is a quantum simulator, what it might do for us, and I'm going to center this near the end of the talk with an experiment that is on the boundary of what cutting edge computation can address. This is something that you're seeing also in the context of general purpose quantum computers, but I'm going to talk about quantum simulators of specific physical systems. So I'd like to start with, when we teach quantum mechanics, why do we start with a particle in a box? So since I can't see you right now, why doesn't, you should feel free to just call out and say why you think we start with a particle in a box.
You can talk about quantized states.
Yes, so it's a simple setting for quantized states. And I would say that, to just sort of build on that, it resembles an electron in a hydrogen atom, which is an electron that's confined in some space, but it's simpler mathematically. And a couple of weeks ago, I was talking in undergrad through particle in a box calculations, and it reminded me about why I was fascinated with this issue. And it's because of, as I mentioned, in my senior year of college, and I was exploring what I wanted to do in physics for grad school, I learned from a seminar about quantum dots or artificial atoms, which I think many of you are now familiar with, tiny nanometer scale boxes that can trap one or a few electrons. And I was shocked to realize that I had implicitly assumed that we could make a particle in a box, because of course we could, because why else would we have spent so much time studying it in quantum mechanics? And I was simultaneously really excited to realize that now we actually could, and that set me on my path for my PhD, and a thread that's gone through some of my work since then. So so in terms of quantum dots, here's an example of one type of early quantum dot where, see whether I can get right my, can you see my mouse? No? All right.
I don't think so.
All right, so I'm going to just wave my hands with respect to that because it seems that I cannot get that to appear. But so there's the small disk between that's labeled dots in this picture, and electrons are confined to a very small dimension in the vertical direction and to a circle in the radial directions. This was one early way to make a quantum dot. And when we talk about it as an artificial atom, part of what that reflects is that if we look at the energies to add successive electrons, these peaks in current as a function of a control parameter gate voltage that allows us to add electrons one at a time, you see that there's an unusually large spacing between peaks when there are 2 electrons, when there are 6 electrons, when there are 12 electrons compared to the neighboring ones. And this is reflecting the shell structure of an electron, in this case, in a 2-dimensional harmonic oscillator potential. So, so let's think a little bit about what are ways to realize simplified models and to realize them experimentally. So if we're trying to, or let me actually just say more broadly than the harmonic oscillator, where I talked about a particle in a box and then fudged it a little bit and said we can build an electron in a harmonic oscillator. What are the reasons more generally that we might want to get a realization of a simple model that is pretty well understood theoretically? So you can call out, and there's no one right answer for this.
Hopefully develop a, say, a building block towards a somewhat less simple structure.
Yeah, so I guess that was Vala, right? So yes, we could establish a building block, and then we put together those building blocks and get something that is that we may not fully understand. So let me just share with you some thoughts that I have on why we might do this. So one example is delight. I would say that applies for the case that I was giving you as an example. It's not that there was anything we really didn't understand, and what was remarkable about building that artificial atom, besides the fact that we could do it, and that it so nicely matched our expectations for a particle or a set of particles in a harmonic oscillator, cylindrically symmetric harmonic oscillator. But it's just, wow, that's really cool. Then beyond that, it could help us build intuition. So maybe there were certain aspects of the theory that were present there, but hadn't really been dug out, and that's something that I'd like to get to as we go forward. And then I would say a third one would be to quantitatively test theory. So how seriously can we take the results of an analytical or computational set of work? And finally, if we can go beyond what's available in theory and computation presently, then we might be able to compute new things to actually use this as an analog computer. And the history of analog computation goes way back. The furthest back I've tracked it is for artillery computations. If you want to know, so often in physics we have some weaponry involved, and sorry about that, but to figure out where a particular shot is going to land. Analog computers were built for that. Electronic circuits were used to model nonlinear oscillators. And I'm sure that there are examples that actually go back to antiquity, well before digital computers. So let me now give an example that I like to say I'm contractually obliged to give in such cases, which is the condo effect. So, yes, there was a question.
Sorry, I have a quick question. The quantitative test of a theory. I have encountered several implementations of Tor models, but there it always seems like you need to do work in order to make the things match. So it's more a test of a platform than a simple theory, which you can frequently also solve directly, right?
So I think, Anton, that's an excellent point. I would like to try to argue that we're getting beyond that in some cases, and that we can actually aspire to say, talk to a leading computational theorist, often using numerical renormalization group, which is sort of gold standard for very low energy computations, and say, we know all of these parameters to put into it. Use those parameters, don't fudge anything, and tell us what gets out, what comes out, and let's compare that to the experiment. But I agree with you that in most cases, that's not how things are done. And I do think that for something to really be useful as, for us to even imagine something to be useful as an analog quantum computer, we would have to do something like that. But I think that there are cases where we can actually do that.
Thanks.
Yes, so the condo effect is a canonical example in many body condensed matter physics, in which there's a single local spin. This is notionally a spin on a magnetic impurity atom that is in a metal. And then there's a collection of electrons, mobile electrons around it in the metal. And at high temperatures or high energy scales, this spin is free and is basically decoupled from the electrons around it. It's, by the way, not obvious that if you put an iron atom in copper, for example, that there will be a remaining magnetic moment, but there are many examples where there are particular magnetic atoms and particular host metals where you do have a net spin at high temperature. But then when you cool down to low temperatures, the electrons around it screen the local spin, and in the simplest case form a singlet. But this is not just like a singlet formed in a hydrogen molecule from two electrons. This is a many-body singlet that involves the many electrons in the metal. And this description, which I'm eliding decades of work on this, where this was first seen in transport measurements in the 1930s, and it wasn't realized that there were even magnetic impurities. It was what was thought to be pure gold. It took to the 1950s for experimentalists to identify, late 1950s and into the 60s, for experimentalists to identify that something was going on with magnetic impurities. And Miriam Sarachik, a wonderful experimentalist who we lost recently, played a key role in that. And then in the 1960s, Jun Kondo wrote down a model of a magnetic moment coupled to a reservoir that described a lot of what was going on. And it turns out that at a more microscopic level, this corresponds to the Anderson impurity model that has one site that can hold 0, 1, or 2 electrons, and electrons can jump on or off. So I guess I spent a little time on this because this is interesting for a number of reasons. The energy scale T condo doesn't appear explicitly in any Hamiltonian, but it follows from a renormalization group argument, and it's very sensitive, exponentially sensitive to the input parameters. And the fact that that it corresponds to the Anderson impurity model is important because it's both a prototypical Hamiltonian in condensed matter physics, and also it's something that we can imagine building out of one of these quantum dots or artificial atoms. So where do we go from here? When I was in early in grad school and was searching for a problem to work on related to quantum dots, a number of theorists, including Yigal Meir, well, not a number of theorists, Yigal Meir and Ned Wingreen advocated for trying to search for a condo effect in a quantum dot, with the idea that if we have one electron in the quantum dot or an odd number of electrons, if it's an odd number, all the spins can pair off, but there's one left over that acts effectively like that magnetic site, and it's coupled to reservoirs that act like the surrounding metal. And this was something that Eng and Lee and Glassman and Reich had suggested some years before, that if you take seriously that you're building an Anderson Hamiltonian, then it should show the condo effect at low temperatures. But Yigal and Ned really advocated for where to look, what was important in trying to do this. So I'm just going to show a relatively recent measurement on this. This is, you don't need to understand all of the details. This is changing a gate voltage that is adding electrons to the system. So here we have, sorry, I'm using my mouse and you can't see it. The horizontal axis is a gate voltage that's adding electrons. So on the left side, you have an even number. In the middle, you have an odd number, then back to an even number. The vertical axis is probing at different energies. And what you see is that with an odd number of electrons in the middle, there's a feature that's right at zero energy, and that's known as the condo resonance, that zero bias conductance peak. Since we're measuring conductance through the quantum dot, that's reflecting a rearrangement of the electrons in the reservoir to screen this local spin. And so why do we need this experiment for intuition? I would say, certainly in retrospect, the system was very well understood, at least by a few theorists in the 1980s. But the experiment made abstract ideas more concrete for a broader audience. So from the point of view of intuition, we could say, all right, here's one magnetic impurity. Let's see what happens when we do X, Y, and Z, even if the theory contained a basically correct understanding of that. But I'd now like to move on to the next step, which I hope can engage with what Anton was raising. So if we want to quantitatively test the behavior of a system, one example in the case of the condo effect is that in the late 1970s, Duncan Haldane had done a simple scaling analysis to argue that the condo temperature should depend exponentially. So you see my formula for TK in the middle of the page. It depends exponentially on some parameters of the system. And I've phrased this in terms of the Anderson Hamiltonian. There's epsilon 0, the depth of the level below the Fermi level, U, the charging energy, the energy to add a second electron, gamma, the tunneling rate. And so there's this exponential dependence. And if you're near, let's suppose you have one electron on the site and you're very far from adding a second electron, then this looks like e to the minus pi times the depth of the level over the tunneling rate. So it's an exponential dependence. And if you wanted to test this or examine it in normal experimental systems, it would be very hard, because what you can do is if you have iron and copper, you could replace it with cobalt and copper, but that's a discrete change. It changes many things about the system. But in this system, we have the hope of changing the energy level independently, the tunneling rate independently, and actually measuring those quantitatively. So what I'm showing you in the bottom left is a plot of extracted condo temperature as a function of a gate voltage on the horizontal axis. I've cut that off, but that gate voltage is tuning the depth of the level below the Fermi level. And what you can see is that the condo temperature is presented on a log scale, and on a log scale, it's falling exponentially as you make the level further below the Fermi level, and then it gets so low that we can't resolve it. And so that's satisfying. This was the first way that one could see it's actually exponentially dependent on these input parameters, but it gets better than that. You can look at the slope of that line, the prefactor in the exponential, and that should be pi, and what we extract is 3.05, which I like to say that the ancient Egyptians had a better value for pi than that, but still that's pretty striking, and that's with no free parameters. We measure and tune the depth of the level, we measure the tunneling rate, and we set a couple of different tunneling rates. I'm showing you this for one. And so that to me was very striking. And so that, for the first time, it made me take really seriously, how quantitatively could we do these comparisons as opposed to just having lots of free parameters. And so I got greedy and said, well, there's this prefactor for the exponential. So first of all, I talked with Duncan Haldane and with other theorists, and they said, all right, this exponential dependence should be basically right. It's very surprising that it should come out to be actually pi there. That was not expected. But this prefactor, which is effectively referring to a bandwidth for the system, some energy scale, that's just maybe order of magnitude. So it's the geometric mean of the tunneling rate and the charging energy. And but I plugged the numbers in, and within tens of percent, it was right. And so that, so I'm not saying that's always going to be the case, but this is a case where we can really treat this as we plug in some directly measured numbers and get out a behavior that is quantitatively matching the theory. And did this teach us anything new besides the fact that a simple scaling relation was remarkably good for this? No, I mean, the theorists who really knew this knew the physics of this, but I think it broadened who could think about it, and also suggested that one could take these seriously computationally.
David, there's a question from the audience from Yigal.
Yes, Yigal.
Yigal, you're muted.
Which is a rare occurrence, but
Thank you, David. I was wondering how the definition of the condo temperature varies, from, you can define the condo temperature in different ways. So I'm surprised that you found the right definition that will match that pi.
Yeah, that's a very good point, and I need to dig back in my memory. So Yigal is of course correct that the condo temperature is just a crossover scale, and one could have different definitions. That I picked a particular definition that was phenomenologically useful for comparing to the data, and so honestly, I need to remind myself what I used for this, for the comparison for the prefactor. So thank you for calling me out on that. And it's possible that that prefactor ends up being slightly accidental, that maybe it would have been a factor of 2 off for different choices. But I think the basic point holds, but I should be careful about how precisely I say without looking back. So, another quantitative prediction for this sort of, and this is one that to me was quite counterintuitive at the time, was that the conductance through a site that had strong coupling to leads like this could be 2 times the conductance of a perfect 1D wire, or the conductance of a perfect 1D wire through which both spins can transmit simultaneously. To explain why that's surprising, well, we should start out with what's not surprising. If you take a Fabry-Perot cavity, even if you make each of the 2 transmissions very weak, if you match them perfectly, you can get 100% transmission on resonance through it. So it's not so surprising that you could get the transmission of a perfect 1D wire or 1e squared over h in fundamental constants through this. But to get 2e squared over h, you'd have to have both spins able to go through as if they were not interacting with each other. And yet we know that on the local site, when there's one electron there, it's very hard to put a second electron on. So it doesn't seem that they should be able to go independently. Now, again, this was something that was well understood theoretically, was understood theoretically, and certainly in, soon afterwards was well articulated in terms of what is the phase shift for the two scattering channels. But to me, it was very counterintuitive that that both spins could go through effectively independently, and that was something that was experimentally demonstrated by Leo Kouwenhoven's group. Wilfred van der Wiel was the lead author on that, and you can see this conductance at low energy that that is touching almost 2e squared over h in a certain regime. So sometimes the comparisons to theory that are quantitative can help with, you know, I really like when there's something counterintuitive and then we can test it. And to me, that was counterintuitive. So, so there are a range of tools to understand materials. And these materials, because they have trillions of atoms, we have to make compromises. And that's okay. All of physics is about realizing we can't solve the problem we started with and instead posing an approximation and solving a problem that we can treat either analytically or computationally or both. And, you know, even the theories of particle physics are recognized now as effective field theories that are approximations in a certain energy regime to some more general theory. So I'm naive in this area and I'm eager to learn and start a conversation, but let me make a cartoon description of tools to understand materials. And since I gave my first talk on this topic at Berkeley, I gave an example from Steve Louie's group of so-called ab initio or first principles computation for a particular material, and that allows for direct comparison between theory and experiment. But there's a limited, you need to think about how to deal with interactions, and generally there's some degree of uncontrolled approximation there. Another choice is to pick a simpler model, not try to deal with many atoms, but something like the Anderson Hamiltonian that I described, one site hopping on and off, never described anything perfectly before these quantum dot systems, but was a reasonably, a quite good description of a small concentration of magnetic impurities in a metal. So I'd call that many body computation. And so there you have a simplified model and you can engage with experimental systems. But as Anton said, there's some fudging or some tuning of parameters there, but you might be able to get a real understanding of how this simplified model works. It's just a matter of how do you map that to the experimental system. So when we think about what nanopatterned model systems have to offer, I would say that they have some real advantages in this space. First of all, and let's say to try to understand quantum phase transitions, so they have advantages that we can design the Hamiltonian, and I'm going to talk about how that works, and then I'll try to go through these various different points. But here's here's an example for designing a Hamiltonian. You see a set of gate electrodes on the surface of a semiconductor that have trapped electrons in two little puddles. I'm showing one is red and one is blue. And then we have leads that we can use to probe them on each side. And this is a real physical object that's made on the scale of some features below 100 nanometers in size. But it also maps onto Hamiltonian that has energy levels on the local site. That's the first term on the left. Sorry, energy levels in the leads is the first term on the left. Then energy levels on the local site that could be spin dependent, the second term. Then there's a charging energy. Putting 2 electrons on that site is expensive. And then we have hopping between the local site and the reservoirs, the leads. We have 2 copies of that, one for the left droplet, one for the right droplet. And then we have an extra term, which is that the 2 interact capacitively with each other. Even if there's no tunneling between the 2, they can electrostatically feel each other. So we can build something that's a quite perfect realization of a Hamiltonian like this. Then once we've done that, we can aspire to measure and tune all of the basic parameters of the system. And so to illustrate that, let me just show you something that some of you have seen before, which is a charge stability diagram. Here there are the 2 axes on the left side are 2 gate voltages that basically tune the occupancy of the two sites, but there's a little bit of cross coupling, which is why lines are diagonal. And so we can label this diagram with the number of electrons on one site and on the other site in each region. And the fact that in the region that I've circled, that we don't go directly, we can't make a tiny change in gate voltage and add 1 electron to each site. We can't go from N1, N2 to N1 plus 1, N2 plus 1, because when we add an electron to one site, there's then an extra cost to add it to the other. So that circled region, which I've expanded on the right side, is where we have 1 extra electron, and it could be on either site or a superposition between the 2. So if we try to make a measurement through making conductance measurements on the 2 droplets of this charge stability diagram, here's what we get. And you can see that it bears quite a resemblance to the cartoon that I drew for you. And what that allows is for us to determine all of the bare parameters of the system, the tunneling rates, the charging energy U, the intersite charging energy U prime, the electron temperature. All of these we can extract from this kind of a measurement. So that's what I meant, Anton, when I said we can determine and even tune the parameters of the system. It's not that I'm at the point where I could predict that if I did the CAD drawings for the gates and I cooled down the sample, that this would be exactly the gate voltage that I'd have to apply to get to these parameter values, but we can pretty directly measure those parameters and then use them as input for a more sophisticated model. So if we want to quantitatively compare to computation, well, I've shown you an example of that, but we can go well beyond that. Here are just some examples from both my group's work and others, including the group of van der Zijpen at Delft, the top left and bottom right, and Frederic Pierre at Saclay, and CNRS in France. And so I'm not going to dig into these right now in great detail, but let me just mention one example that I think is intriguing, the one on the top left. This is an example where there are 4 sites, and they were aiming, well, I think they were aiming to study a particular piece of physics, or maybe it was just serendipitous, but they chose to study an old toy problem that I think many of us have found intriguing, which is called Nagaoka ferromagnetism. If we have an array of sites and hopping between them and charging on each site, so basically a Hubbard model, and we have 1 electron on each site, then the system likes to be antiferromagnetic because electrons can spread out a little bit more if their neighboring sites have opposite spin. But Nagaoka pointed out that if you take one electron out from this, put one hole into this lattice, then in principle that should make the system ferromagnetic. And basically, electrons will be more mobile if their neighbors have the same spin. So we can talk about that more if you have questions later. It's not clear what relation that has to any realistic material system. We know that putting one hole into a Mott-Hubbard insulator does not seem to make it ferromagnetic, but on just a four-site basis, they were able to put one hole into that four-site and to probe directly that the other three electrons then aligned their spins, which is pretty cool. Another example is the two-channel condo model, which is where electrons, a local spin is screened by two reservoirs, and they can't both form a singlet with it, so it's a frustrated system with a phase transition. That was also studied by Frederick Pierre in a different realization that we're going to get back to, based on charge playing the role of spin. And he showed a beautiful example of concrete experimental realization of renormalization group flows, which I'd never seen before. Finally, this is just a Fermi-Hubbard model with several sites and trying to look at whether you get an insulating state when you have one electron in each site. So these are just examples of how people are building up few site correlated electron physics behavior. So another advantage of this is that one can locally probe each site. So an example from the Hubbard case is that you could look at the charge on each site and electrons jumping on and off with a nearby capacitive sensor. There are also ways to try to probe each site by conductance, by measuring density of states by tunneling. So there are disadvantages. It's hard to scale this to many sites. Every site is going to be different from every other. And to some degree, you can't get every Hamiltonian that you want. And so you've noticed I am talking about quantum simulation, and I haven't been talking about the elephant in the room, which is cold atom gases in optical lattices. And that's a very rich set of systems and very interesting. And we can talk more about what solid state realizations have to offer, what atomic realizations have to offer. But certainly this is one place, scaling to many sites and being able to make a lot of different Hamiltonians. That's something those are strengths of the atomic systems. So I'd like to now introduce a sort of new system that our new experiments are built on. So it's only sort of new. You see that the citation that I give is to work from 1990, 1991, very creative work by Kostya Matveyev, showing that if you have a metal grain that's pretty isolated from its environment and could have two different charge states, that those two charge states can act like the spin in a condo system. And then there can be a mapping in which you could study condo physics in that system. And I'm not going to get into the mapping in great detail because it's a pretty nuanced thing, but let me just say that there are some important requirements for trying to realize this system that explain why, despite a lot of effort, there was not success in the years after Kostya introduced this. So you have to have a large charging energy. So electrons, you have to be able to mostly be sitting in a situation where there are two charge states accessible, but not higher charge states. So that means charging energy much bigger than temperature. You need to be able to couple through one mode to a reservoir or a few modes, but with each tunneling controlled, you need a large density of states in the grain, so you don't want single eigenstates, single distributions of where the electron lives to play an important role. Instead, you should be in a superposition of those. These are things that some of them can be done really well in semiconductors. For example, the precise control of the tunnel couplings. Others can be done well in the metals, the large density of states in the grain, but you can't get it all in one of those systems in most cases. So Frederick Pierre came up with a really clever idea a few years ago to take the best of semiconductors and the best of metals and bring them together. And so what he did was to take a metal island, which those of us in the semiconductor world know as an ohmic contact to, in this case, gallium arsenide, and he made it a few microns across. This was not the first time people had made such small contacts. Perhaps this was even, I'm most aware of work from Moti Heiblum's group at the Weizmann Institute in Israel, but others have made small ohmic contacts. And he coupled these to regions of semiconductor and controlled the coupling to these broad regions with quantum point contacts, with split gates that could tune down to just allow one mode and tune the transmission through that mode. So what you can see in this picture is that there are 3 quantum point contacts, and those allow you to have up to 3 modes coupled. And this he also chose to do this in the quantum Hall regime in high magnetic field, so that you'd have a well-defined one-dimensional mode connected. And what I'm showing on the right-hand side is I alluded to a renormalization group flow. And if you look in the middle right, the system, when you tune certain parameters, can flow toward this this cross, this intermediate coupling fixed point, and that has a particular characteristic conductance through the different leads. And I found this really invigorating, because I had never seen an experimental system where one could really visualize a renormalization group flow. Again, that may simply be because of my ignorance. And there were also puzzles in this, like if you look in the top left, you get conductances over 1e squared over h, which naively shouldn't be possible in this system. But in any case, Frederick pioneered this system, and I looked at this and felt, that's really beautiful. I'd have loved to have come up with that, but more than that, maybe there's something that we could do with it, extending it. And so I thought, well, let's put 2 of these islands together. And so if we do that, the reason that I thought of it was the idea of having effectively a magnetic impurity on the left, a magnetic impurity on the right, and we could study what's called the two impurity condo problem, which was studied importantly by Barbara Jones and Chandra Varma, and also by many other theorists, and has been thought of as a step toward understanding heavy fermion systems, condo lattices, just having 2 sites coupled to each other into reservoirs. And for reasons that I don't have time to get into, it's been really hard to find a way to realize that in quantum dots without taking what should be a quantum phase transition and turning it into a crossover. And so I thought, aha, finally a way to make 2 impurity condo. It turns out, no, this isn't 2 impurity condo. It's something different and in some important ways richer and more interesting. But I remain frustrated in my attempt to do 2 impurity condo. And so if someone has great ideas for doing that, I would be excited. So this work was started in my group by Lucas Peters, a grad student who's since graduated, and then brought to some beautiful fruition by Winston Paus, who's a senior student in my group, and then there are other students, including I'll mention this later. So we can map out, like I showed you before, charge stability diagrams in this system. And on the left column, I'm showing you experimental data. And the right one, I'm showing you numerical renormalization group calculations by Andrew Mitchell for comparable situations. And on the far right, it's if we could get to very, very low temperature, what we should see based on the calculations. And what I want to emphasize is that there's really quite a good match between the experiment and theory. And basically, there's no freedom in this. We measure all of the parameters of the system, but there is one fudge here, which is that what we're measuring and controlling in the experiment is tunneling rates through transmission probabilities through a quantum point contact. And what the theory deals with is the J, the coupling between spins or effective spins in the system. And I hope that we'll be able to push through and really get the mapping between the two, but it is a bit complicated. And so that's one freedom, that they should be monotonically related, but it's not clear exactly what's the relation between our tau and Andrew Mitchell's J. So we can look at, I like to say that color plots can show you, can make things jump out for you, can show you a lot of things that you didn't expect, but they can also hide a multitude of sins. So I like to look at line cuts. And so here are the direct comparisons of line cuts. And you can see there's not a perfect match between the experiment and the renormalization group calculation. That might be because of the number of different charge states that end up important in the experiment that the calculation can't fully keep up with. But you can see there are a lot of qualitative matches between these. And the first thing that I'd like to now dig into is, can we see that there's a competition between different interactions, between the interaction between the two local sites, which turns out to be a condo interaction, not a simple antiferromagnetic J, the interaction between the two local sites on the one hand, and the interaction of each site with its neighboring lead on the other hand. There should be a competition between these, and you should only get transport should be maximized when the two are balanced with each other and not when one wins. And so here I'm showing each line is for a different tau value, a different value of the coupling to the leads. And then the horizontal axis is changing the coupling between the two sites. And what you see is that these curves tend to have a maximum at a particular coupling value, tau c, and that maximum moves to higher tau c as you make tau bigger. And that's what you'd expect to balance the two. So, if we, another thing that we could do and try to compare with theory on is there a universal conductance curve? Is there some energy scale, which we'll call T star in this case? And if we look on the left side, how the conductance falls off as we go down below T star, basically below T star, we can tell that there is not a perfect match between the two couplings that I mentioned, and then you get no conductance. And so we could look at temperature much bigger than T star or much smaller than T star and try to look at universality there. And so to do that, we would need to get a handle on what controls T star and how do we go from T star equals 0 to some higher value. So if we look at this curve where we're from the left to the right, we're adding a total of 2 electrons to the system. In the middle, we've added 1 electron. On the right-hand side, we've added the second electron. And sitting on the peak here, notionally, we're at the triple point. We're at the point where there are 3 possible charge states of the system: an extra electron on the left, an extra electron on the right, or an extra electron on both of them. So there are 3 charge states that are basically degenerate. And as we move away from there, in what I'm calling U tilde, T star should go up theoretically as U tilde to the 3/2 power. And T star should also have a component from our not perfectly matching the two tunneling rates. And so we can look at the measured conductance as a function of the T star due to these two perturbations that add together. And what you see there is that indeed for different couplings between the two dots, each type of symbol is for different couplings. We can collapse these all with no free parameters onto a single curve, and it also matches a computational calculation that's a little bit off from the universal calculation because we're never able to get to the two taus perfectly matching. So another thing that we could look at is scaling behavior with temperature. So with temperature and T star. So if we look at detuning in T star, but at different temperatures, everything else being the same, you see that conductance falls off differently as you go away from that peak I showed you. But if we scale T star to the physical temperature of the system, what you see is that these actually all collapse onto one curve over a certain range. Again, there aren't free parameters here. And so what we've seen here, and these collapses are highly non-trivial. The power laws are not simple first power or second power, they're 3/2 power. We didn't say what's the best power to put in. We just said, let's take the power from the theory and run with that. So we've discovered a new quantum phase transition. That discovery, I'd say, in a certain way, was made by Andrew Mitchell, the theorist who did the NRG calculations, who pointed out, first of all, that we hadn't made two impurity condo, but he did all these computations, and then we can see experimentally matching to cutting edge computational work that took days on supercomputers that we see that the expected collapses occur, and we've identified this new quantum phase transition. And that's an interesting, I would say, liminal space from my perspective, because we're right on the border of what can be done computationally with that technique, with NRG. Now, it might be that people come up with better algorithms for NRG that give us orders of magnitude more, but what Andrew says, and I think he really is at the cutting edge, he said, the device that we built, we could add an extra channel to each side, and that would be 2-channel 2-impurity, some kind of condo system. He said that would be too much. It would then be beyond what could be computed in any reasonable time, even on supercomputers. So we're right at the boundary. Even with our existing device, we could make measurements that there's no way to validate, at least with NRG, to my knowledge right now. And so I'd be interested in, are there other computational techniques that should be considered in that range? Quantum Monte Carlo or others. And also, what do we do when we get our wish and we can go beyond, we can make something that is computationally meaningful and goes beyond what classical computers can calculate, but how do we benchmark it? How do we decide what's meaningful, even if we've already determined that we really know the values of the parameters that we're putting in? So that's, to me, a big question. I'd like to acknowledge the people who've done such great work on this. As I mentioned, Lucas Peters and Winston Paust were the two students who made the big contributions there. Andrew Mitchell did the theory. Mark Kastner, my former thesis advisor, and now someone who contributes a tremendous amount hanging out with my group in his retirement. The materials were grown by Ulf Denzer and Antonella Cavana, and we got a tremendous amount of help from Frederick Pierre, who we would keep asking questions as we hit walls. Andrew Keller did some of the work that I showed early in this, and two of my current students, Praveen and Connie. Praveen is on the call now, and I think Connie probably isn't, but are carrying this forward, and I'll mention that in the Outlook section. And I know we're right at the end of time. This work was made possible, the bulk of it by the Department of Energy through the Stanford Institute for Materials and Energy Sciences, though this is really building on 20 years and more of work that was supported by a number of different organizations. So where are we? We can add a second channel for each site, even with the existing sample. I told you that that's beyond what can be computed to my knowledge. We could add a third site. I think that would be quite exciting to get frustration by a triangular arrangement and see what happens if we stop it from being frustrated. I said that if you make many sites in this sort of system, everyone will be different, but I think now for the first time, we can tune them and know that we've tuned them to be all effectively identical, unlike lattices of quantum dots where the quantized levels in each dot are going to be different. There are major technical challenges, but if there's a good reason to do it, I think there are no clear roadblocks, but it would be a real investment. And so I want to do it if there's a good reason to do it. And finally, there are these open questions about, suppose we do all of this, what is it going to mean for understanding materials? And I was interested that Philip Broning said, maybe we could get a handle on coherence in heavy fermion systems. And I think that there's some real hope for that. So I'd like to close with that and welcome questions.
All right, thank you, David. Indeed, if there are any questions, please go ahead and raise your hand.
So Yigal, I think your hand is raised.
Okay, first, thank you, David. That was really exhilarating. I wanted to ask you something that bothers me about this measurement, not directly related to what you presented, but this is something that we work on. I mean, you mentioned in your last line the specific entropy, specific heat and entropy using Josh Fox's method, which is something we work on together.
Yes.
And one of the problems, in all these measurements that you describe, is that when you say, you probe the system, right? I mean, you presented this charge diagram, for example, for the two-dot system.
Yes.
So I assume that you use the same method as everyone. You have like a quantum point contact, a quantum dot nearby, and you drive current through. So you couple your system, your quantum system, to another system which is out of equilibrium. And you assume that this other system probe your system at equilibrium. And there is evidence that this is actually not the case, that you can induce transitions between the two dots, for example, and you get some telegraph noise as a function of the current in your QPC.
Yes.
And this becomes even more serious when you want to probe strongly correlated state, like a condo effect.
Of course.
And I mean, we studied this. I mean,
so absolutely, that's a very good point, Yigal. I do think that those charge sensors, those capacitive sensors, are very useful, but you pointed out pitfalls with them. Actually, in all of what I presented, we're not using those. Everything is linear conductance and differential conductance. And in the last part of what I was talking about, it's really focused on linear conductance. So it's, I certainly would not guarantee that we're not perturbing things through the environment, but it's not directly by such a concrete measurement. We're applying a tiny bias across from one lead to another and measuring conductance, not measuring the capacitive sensing. But I do think it's really important to think about how you affect a system by your measurement and what are different ways to do it. So Anton?
Yeah. So also speaking of perturbing the system with measurements, so for you the control knob is temperature, which is quite all right. Has there been any works, or do you have any ideas about using weak versus strong measurement, or measurement strength as a way to achieve this similar effects?
So that's a really good question, Anton. Asking, can we control the strength of our measurement? That would certainly apply to these capacitive sensors, and you could easily control that by how much bias you put on your charge sensor. And I see that Jens is raising a hand, so just in a moment. I'm not sure what would correspond in terms of my directly tunable knobs, what would correspond to weak versus strong measurement when we're measuring conductance through the system. But certainly we're trying to be in the limit of linear conductance because it turns out we heat up the islands, these metallic islands, if we go to high bias. But broadly, it's a really interesting problem. I also, before going to Jens, I just wanted to say, Michael Seder had posted at some point, it can be solved exactly, but I no longer remember what I was talking about at 1037.
That was about the quantum dot model in Intro to Quantum courses.
Got it. Yes. Oh, absolutely. All right. Agreed. So Anton, did you have anything else you wanted to?
Yeah. So I was wondering because the measurement is also a way to limit long time correlations similar to temperature. It also introduces a time or an energy scale into the problem. And that's why I was wondering whether that would be a more controllable knob.
Yes. So maybe we can talk about that more offline. Maybe there's something we could do with the reservoirs. I've certainly thought a lot about, condo box and shaping the density of states in the reservoirs, which does provide a cutoff like that. But in this particular case, I'm not sure that I see how to apply this, but I think it would be really fruitful to discuss. So Jens, are you still there?
Yeah. No, I was just queuing along the lines of using this as a simulator. There's, let's say we understand most of the condo effect, and then there's the more advanced versions that you showed here towards the end, where you were kind of at the boundary of this. But if it comes to understanding, let's say, d-electron materials,
yes,
it could be really interesting perhaps to make multi-dot simulators, a little bit like is being done, you could say, on a surface of superconductors with atom chains.
Yes.
There you get bands of let's say, synthetic d-electrons, let's call them dot electrons in this case, where you could start looking into heavy fermion-like stuff and hybridization physics that's very hard for us to work out otherwise. Any ideas along these lines?
So Jens, I agree completely. And I believe that right now, in terms of building those, so first of all, as you probably know, given people you've hung out with, it would be no problem to build 100 of these sites in terms of the gate electrodes. It is challenging to tune them all up, but in this metallic island coupled to semiconductor, it's actually possible to do that tuning and know that you've done the tuning in a way that's not possible in arrays of quantum dots, because of everyone has impurities in different locations, is lithographically different. But with the metal islands, the continuum of levels means that we can get around that. So we can imagine making an array of these sites, a 1D array. I think that 10 is within striking distance, though it may be, two graduate student theses along the road. And I think it's worth, in the meantime, thinking about how to interpret this and what it would mean. But I do think Andrew Mitchell's insight that the coupling between the sites is actually a condo coupling opens the way to actually get coherence in the effective d electrons along the chain in a way that you couldn't get from the two impurity condo system. So I really hope it's possible, but it's going to be a big push to do it. So we need to have discussions with you and others to inspire that.
Yeah, it could be fun and educating.
All right, are there any further questions? If not, I have one, maybe not exactly a question, but a small comment on one of your early slides about, why pursue nanopatterned model systems. And it's kind of implicit in both the talk and I think in all the discussions that we've had so far, but like the first bullet point might be that they're fermions that we're dealing with, which immediately means that things are hard already in a lot of ways computationally. So, we also have a lot of other sort of tunable, designable, exactly measurable Hamiltonians, particularly like, for example, with electromagnetic circuits and so forth. But working with fermions adds a whole other layer that I think is quite nice.
Absolutely, I'm very fond of fermions, and thank you for pointing that out, Fala. I guess that so I think that that's right. But again, I think there's the question, okay, suppose you do it and it all works, so what? What have we gotten out of it? And that's why I tried to lay out this taxonomy of, there's the space for delight, for building intuition, for quantitative tests of theory, and then for meaningful computation, and seeing where in that space we have hope to, what does it mean to understand a material? Is it that we can then design another version of the material that would be different in some way? I spent a year doing history of science at the end of my undergrad, and one book that I read that really shaped my thinking was called Representing and Intervening, and by Ian Hacker, and he said, you really, what does it mean to know that something exists? It's that you can act on it and do things with it. And so he gave the example of a muon. When was it that we really knew that muons existed? It was when, sort of like throwing a baseball, you could intentionally send a muon from one place to another and get it to do something. And so I do think that we build our understanding through acting on things, but I feel like, there's the world of complex materials where wonderful things are discovered. And there's this world of building model systems where we get rich behaviors. And I'd like to try to see how much those can be in conversation with each other, as opposed to each side just across a chasm admiring the other.
Wonderful, thank you. I think that will conclude us for the day. Thanks again, David, and we'll look forward to seeing everyone we're not in 2 weeks, but in 3 weeks, when we will have Corentin Coulet in for the next colloquium. Thanks again.
Thank you.